So continuing in Chapter 4, Applications of Trigonometric Functions, we're going to look at Section 4.2, the Law of Sines, an extremely useful law. So the first objective is going to be to solve SAA or ASA triangles. So this abbreviation means side, angle, angle, or angle, side, angle. So that's what the abbreviations mean, and as we go through each one, I'll show you what that arrangement means. So objective 2 is a little different. We're going to solve SSA triangles, and your approach needs to be different for those. So that's why this is separated into 2 objectives. And then there's tons of applied problems we can use the law of sines for. And in fact, you'll see some of the right triangle problems we've already done. The law of sines makes them easier. So the first objective is going to be to solve SAA or ASA. So side, angle, angle means you know 2 angles. So say you know angle A and angle B, and then it's the side that's not in between them. So it would be ASA if it meant the side in between the 2 angles. So that's a different case. So this is if you knew side length B or side length A, then this would be an SAA triangle. So angle side angle, so this one's SAA. Angle side angle is if you know 2 angles and you know the side in between them. So you know 2 angles and the side in between them, then that is called ASA triangle. So they're solved in the same way, so they're included in one objective. So an oblique triangle is the name for a triangle where none of the angles is a right angle, and then the triangle itself is called oblique, a word you don't run into very often. So there are 2 types of oblique triangles. It's possible that all 3 angles are acute. So in fact, the 2 examples that I drew over here both have all the angles smaller than 90-degree angles. So you can see how that would be the case if you make the 90-degree angle a little smaller even, and the other angle is a little bigger, then you can get an oblique triangle. Then you can also have an oblique triangle if one angle is obtuse. So remember that means bigger than 90 degrees. And 2 are acute, so that means smaller than 90 degrees. So you have a triangle with a really big angle and 2 tiny angles. So here's the big obtuse angle. So you can see how it's very different looking. So remember that solving a triangle means find the lengths of all of the sides and the measurements of all of the angles. And we're going to round side lengths to 2 decimal places. And angles round to 1 decimal place. And you might just write that over and over again until it's second nature. So as before, round side lengths to 2 decimal places and angle measures to 1 decimal place in degree mode. So you have to be given 3 pieces of data in order to solve a triangle. So there's actually 4 possible scenarios. So you have to be given 3 pieces of data, but there's 4 possible ways this could happen. So you're going to use the law of sines if one side and 2 angles are known. So the 2 different arrangements are ASA or SAA. So those are illustrated here. Here's ASA, where you know the side in between the 2 angles, so that's the name that's given to that triangle. Then you have the SAA case where you know 2 angles, but you don't know the side that's in between them. You know one of the other sides. So if you know 2 sides and the angle opposite one of the sides, that's the SSA case. So you know 2 sides and the angle opposite one of the sides. So you don't know the angle in between them because that would be SAS. So you know two sides and the angle not the one in between them. So that's the second scenario, and use the law of sines for that. Then in section 4.3, we're going to learn the law of cosines, and you use the law of cosines if you know two sides and the included angle. So that's the SAS. So you know two sides and you know the angle that's in between those two sides that you know. And then you're going to be using the law of cosines because you don't have the information you need to use the law of sines. So it's going to be quite obvious when the law of sines doesn't apply. And then if you know all three side lengths and no angles, again, that's going to be using the law of cosines. And again, it's going to be very obvious that you can't use the law of sines. Once you learn it, you'll see the arrangement that you need to have for it to apply. So you're going to use the law of sines if you know one side and two angles, or two sides and the angle opposite one of them. Use the law of cosines if you know two sides and an angle, or three sides. So here's the law of sines. And it's a really important relationship, and the proof is actually in your book. And it's important that you understand why this is true, that it's not just something somebody made up, okay? This is true for every triangle, that if you look at the ratio of the sine of angle A to the side length opposite angle A, that's the same ratio as the sine of angle B divided by the side length B, which is also the same as the sine of angle C divided by the side length C. So it's actually three separate equalities: A to B, A to C, and B to C. All of those are equal. So we're going to use a lot the fact that for every triangle, A plus B plus C equals 180 degrees. So remember at day 2, I'm pretty sure we tore up triangles and laid the angles together and saw that, sure enough, they always add up to 180 degrees. So let's look at an example of an SAA triangle. Let's see why we know that's what it is. So I have A is 50. Here's my little chart that I'm going to fill in. A is 50 degrees. Make sure you put every appropriate degree symbol so I can tell you know whether it's degrees or side lengths. And we have side length A is 3. So if we know the angles have to add up to 180, then we can see that angle B is equal to 110 degrees. It's not approximate. It's equal because the angles must add up to 180 degrees. So now I can see that this triangle has one really big angle, angle B. So I'm going to draw a triangle with a big angle, angle B, that's 110 degrees. Then this looks like the smallest angle, so I'm going to label it angle C, and this is side length little c. Side length little b is across from angle B. And then angle A is 50 degrees. So side length A we know is 3. So the law of sines tells us that the sine of 50 degrees divided by 3 is the sine of 110 degrees divided by side length B. So then you can either cross multiply, because this is a proportion. When you have two ratios set equal, that's a proportion, and that's the setup when you can cross multiply. So you can have B times the sine of 50 degrees equals 3 times the sine of 110 degrees, and you're going to see that if you divide both sides by the sine of 50 degrees, then you're going to get an approximate number for side length B. So I'm going to take the sine of 110 degrees times 3, and I'm going to divide it by the sine of 50 degrees, and I'm getting 3.68 because we're rounding to 2 decimal places. And I'm going to put approximately equal because I calculated this, so it's an approximation. Now you cannot use the Pythagorean theorem to find the third side length because this is not a right triangle. So this looks like it erased. This is an example of an SAA triangle because I knew two angles, A and C, were given to me. but the side length I knew was not the side length in between, so it wasn't an ASA. Okay, so then are you seeing how you can solve for the other unknown side length B? And always use a given value when you have a choice rather than a calculated value. So I would go back to sine of 50 degrees is to 3 because both of those numbers were given. And that's going to equal sine of 20 degrees is to side length little c. So again, we have a proportion. So that says c times the sine of 50 degrees equals 3 sine of 20 degrees. And dividing both sides by the sine of 50 degrees, we get that c is approximately equal to 1.34. So 1.34. And now take a moment and look at the triangle and see if this seems reasonable. So it looks to me like my side length B is longer than side length A. So that seems reasonable. And it looks like side length C is smaller than all of the other side lengths because that angle C is smaller. So this seems reasonable. So at least make sure it seems like it's in the ballpark and that you don't have some crazy numbers. Okay, so we'll do this next example in class together so I can see how you're doing and comment on your work. And then let's do objective 2, which is solving an SSA triangle. And I'm going to make a separate movie for this one because this is a special case that will come up, and it's called the ambiguous case, and it takes some care working on it. So I want to give it plenty of time so that we can be really clear about it. So this is going to be the end of 4.2 section A, and then I'm going to make a B part movie for the rest.